Okay, well, welcome back. This is video number 2. So we've done the introductory video. You've watched the introductory video. You know what the videos are about and the expectations. This is video number 2, where we're actually going to start content. There's a couple of important things just to keep in mind. Right here, this alphanumeric code, 1.A.1, that refers to the AP Chemistry Framework. So you should have gotten a big packet, a framework packet, of what the AP College Board expects you to know going into the test. This refers to that packet. So 1, that's the unit. We're in Unit 1. We're in Big Concept A. Okay, so the big idea is A, about atomic theory. And we're in the first subset of that. So we're in Unit 1. We're starting with our very big first concept A, and we're in the first concept idea right there. Okay, and this concept is atomic theory. So the way that AP Chemistry works is we spend the first semester talking about the atom and what the atom is and what it's made of and how it acts. And then the second semester is all chemical reactions. The energy put into a chemical reaction, whether a chemical reaction will occur, what's happening during a chemical reaction. So before we start talking about anything, we need to just talk a little bit about atomic theory. This should be a review not only from honors chemistry, but also probably middle school. So we're just going to kind of move pretty fast. Okay, there's a couple of things that is true about compounds. The same compound has a uniform composition. So let's say I have water. So for example, I have water, H2O. The composition of water is always uniform. It is always 2 hydrogens and 1 oxygen. It doesn't matter if I get water from Lake Michigan or the Nile River or the Indian Ocean. Water is water. Water is H2O. Now there might be other things mixed in, but that's a mixture. We're not talking about mixtures right now. We're talking about the compound. The water compound is H2O. It never changes. Okay, so it's uniform composition. It is the same thing every time. So, what we can say then is, or one conclusion we can draw from that is, the average mass should be constant. So the average mass of a whole bunch of water molecules should be the same. I'm trying to find a spot to stand so I'm not kind of, so you can write it, but I'm not off to the side. Never mind. So the average mass of a water compound should be the same. Okay? Now, that's for large samples. Now, it's true since we have isotopes, they might be slightly different if we're looking only at one individual water molecule versus another individual water molecule. But large amounts, a mole of water, will all have the same average mass. It'll all have the same average mass. So that means if I have a compound and I know the mass of that compound is 18.02, I know that compound's probably going to be water. Now there's other tests we can do, but that's it. The mass of a compound is the same. All right, so one water molecule doesn't weigh a different amount than the other. And once again, that's only true for large amounts. That's only true for large amounts. Okay? Meaning billions of molecules or billions of atoms. If I have only one, I'm looking at isotopes can cause those masses to vary, but we're looking at large amounts. And the good news is that it's really hard to look at small amounts, so we always look at big amounts. That works out great for us. Okie dokie. Let's do a quick little diagram of a pure substance versus a mixture, and I'm looking at something to erase it with. Here we go. All right, so let's talk about a pure substance versus a mixture here really quickly, because I mentioned mixtures when we were talking about how different waters can be slightly different. Like let's say if I take a big swig of Lake Michigan water and it tastes different than like a bottle of Ice Mountain water, that's from all the fish poop and the other stuff that's mixed in to Lake Michigan water. Fish poop probably being the best part of it. Okay, so pure substance versus mixture. So we're talking about pure substance versus a mixture. Now, you've probably seen this chart before in honors chemistry, and even then it was probably a review. So I'm going to kind of slap it up here. I'm not really going to discuss it very much because, once again, this should be a review. Okay, so let's say we have this little chart, pure substance versus mixture. If it's one compound or one type of compound, that says compound, it's a pure substance. If I have multiple compounds, then it's a mixture. Okay? Now, pure substances can be broken down further. If the compound is only made up of one atom, we call that an element. There's a whole table of them. You'll figure it out. So if the pure substance only has one atom, it's an element. If it has multiple atoms, it's a compound. Or we call this a molecule. There we go. I use a little weird looking. There we go. It's a compound or a molecule. These multiple atoms must be chemically bonded together, right? It must be bonded together. Otherwise, it would be a mixture. It would be multiple things. Okie dokie. Let's say the mixture. Now this one, for some reason, throws the most people. If it looks the same, if I hold up a beaker of a substance and, oh, it looks pretty good, it looks the same, it's homogeneous. Or homogeneous, if you prefer. A little hoity-toity term. Homogeneous. If it looks different, it's heterogeneous. Or heterogeneous. Heterogeneous. I don't, that's just officious. So if it's a mixture that looks the same, it's homogeneous or homogeneous. If it looks different, it's heterogeneous or heterogeneous. Okay? And then once again, if it's only one atom, it's an element. Multiple atoms, it's a compound. Alrighty. Moving along. Okay. Should be pretty straightforward. Mixtures can be separated physically. Alright, so if I have a mixture of multiple compounds, I will do physical processes to separate them out. That could be something like filtering it. That could be something like distilling it. That could be something like evaporating or boiling off the liquid. Chromatography is separating out liquids based off of how quickly they move through paper. So, like if I wanted to separate out the dyes in this ink, it would be chromatography. Okay? Those are physical separatory techniques. I am not changing the substances in any way. If I boil water, let's say I have a beaker of salt water, and I boil the water off, I still have water. It's in the form of steam, but it's still water, and I still have salt. I haven't chemically altered those compounds in any way. On the other hand, pure substances must be chemically separated. Alright, they must be chemically separated. So for example, let's say I have water, I have H2O. If I want to separate out my oxygen and my hydrogen, what I do is I pass electricity through it. And that electricity breaks these bonds. So I'll be left with oxygen and then a hydrogen molecule. Okay? So I will break these bonds and I'll be left with oxygen and hydrogen. This is no longer water. This is oxygen and hydrogen. And in actuality, we get oxygen diatomic as well. But we get oxygen and hydrogen. Oxygen and hydrogen. That's no longer water. Oxygen and hydrogen aren't water. Both of these substances are flammable. This is explosive. They filled the Hindenburg with that, and it exploded. They filled Apollo 1 with that, and it burned. Whereas this, water is not. Right? Water will put fires out. Very different properties, different compounds. Chemically separated, mixtures can be physically separated. Okay? So that is going to cover video number 1. All right, so that was topic number 1. Hopefully it was a review. Hopefully you understand it fairly well. And have a wonderful rest of your day or evening. Thank you.